Good day, everyone. My name is Justin Patts, and I'm a researcher at the National Institute for Occupational Safety and Health, a division within the CDC aimed at improving worker health and safety. Today I'm going to talk about my concept, which would aim to better quantify the hazards in air within industrial plants. Certain types of respirable dust, especially those with silica, are incredibly toxic. For example, if you aerosolize the mass of a quarter in the volume of the Rose Bowl Stadium, all of the occupants would be overexposed. Respirable dust is so small that your eye can't see it. The background image shown here is from our scanning electron microscope and focuses on some silica particles that we recently collected at a plant. Note the scale on the bottom right. So the handful of dust specks that you see here are between 2 and 6 micron in diameter. To put that into perspective, the diameter of a human hair is about 60 micron. First, a little about silica and disease. So what is the big deal with dust? Well, not all dust is the same. Some dust, like what is in your house, is largely regarded as nuisance because it lacks toxic particles. Some dust, however, can cause debilitating disease. You've likely heard of coal miners' pneumoconiosis, or black lung, but maybe you've not heard of silicosis. To put it into perspective, the allowable limit of respirable silica is some 30 times lower than it is for coal. Workers who are dealing with the cutting, blasting, or abrading of materials containing silica, like construction workers or miners, can be in the presence of very high concentrations. There have been several huge silicosis tragedies in the last century. In 1931, nearly 500 workers died when blasting a tunnel for the Gauley Bridge in West Virginia. And even just recently, NPR had a story on the high rates of silicosis in the Appalachian coal region. It's a disease that is 100% preventable, but the key is you have to know how much is there. In this short presentation, I'm going to discuss the problem that I was trying to solve, the proposed solution, and some metrics for how I would evaluate the performance of the robotic system if it was actually integrated and tested. The key concepts that we have discussed in class are addressed, including the cost and economic justification of automation in robotics, the level of automation, accuracy required, kinematic chains, navigation, programming techniques, and sensors. I'll conclude with a look forward as I attempt to develop this concept beyond this class. Silica exposure is quantified by two general techniques. The first is what is termed gravimetric sampling. Here, dust is drawn through a cyclone that size separates it, so we're depositing only the respirable fraction onto a filter for post-weighing analysis. This is the only method that is used for compliance enforcement. That is, when a government agency checks the conditions, they rely on the most reliable measure for personal exposure. But the mass concentration is just one number, and it can't tell you how high or it can't tell you when high exposures happen during the work shift. For that information, recording dust monitors can be used. Those are pictured in the middle, and there's a few varieties. They use scattered laser light to estimate the particle concentration. They're very repeatable, but unfortunately they have a serious drawback. They cannot be considered to be very accurate and must be corrected because of the variance in particle optical properties. Even on the same material, size can be a factor. In addition to personal sampling, area sampling can be used. Sometimes you don't need the worker's exposure, you want to monitor a particular zone of the plant instead and look for which machines or processes are emitting dust. Area dust monitors are basically optical particle counting instruments in a weatherproof enclosure, and as such they're on the order of the cost of those instruments at about $8,000 each. This means they're expensive and still subject to the same issues that all light scattering instruments have. So because of these cost and accuracy limitations, you won't see a case where enough area monitors are used to identify particular dust sources. I've talked about how you sample, but not how much. The fact is that workers in these industries are sampled very rarely. If the health effects of silica are resulting from cumulative exposures, which the literature says that they are, we need to have ways of quantifying the plant's dust environment on a more continuous basis. In your business, you understand that production, personnel, tasks, and environment can change a great deal day to day. Compliance sampling cannot quantify these cumulative exposures. Internal company audits also provide just a snapshot of activity. The decision to invest in engineering controls is a big one, but one that mining companies are willing to take if they know with great degree of confidence that the intended solution was actually going to reduce the dust exposure of the workers. The ability to quantify and measure is key. We all know that robots are very useful in performing repetitive tasks that would be too burdensome for humans, and as long as the dexterity required is not too great, robots are usually more repeatable too in these tasks. Here we have an outdoor mobile robot that was tested in Europe to identify gas hotspots. This robot uses LiDAR and odometer for spatial location and collects airborne gas measures like methane, CO2, CO. It also collects 3D wind speed and direction, which can certainly impact the gas readings. The output of this robot are concentration maps and source identification, and the robot is the only source of concentration data in the system. In the last example, we saw a ground-based robot, and you can imagine that could be useful maybe in an oil refinery. But what about an open pit surface mine, where they have large concentrations of blast gases widely dispersed? Here we would need an aerial robot, and that's just what an Australian firm has demonstrated here. The authors used a modified low-cost board-level optical dust sensor to map 3D airspace dust concentrations. They demonstrated the concept by releasing fine talc as the source dust and correlated the results to a calibrated dust instrument. Here the robot collects all the concentration data in the system. Professor Walks has introduced us to many types of robots this semester, and they range from technically feasible to very proven, having been used in industry for many years. Here we have an established company in California that makes and sells these mobile security patrol robots. They have the ability to autonomously navigate obstacles, climb curbs, stop for vehicles, and yield the right-of-way to pedestrians. The robots are primarily autonomous and start around $40,000. I'll be visiting their factory later this year to see if they could possibly work in this application. So I've shown in the literature that mobile robots can map environmental gases or dust, but for exposure to respirable silica, we need a continuous measure in a fixed location. It's pretty useless to have spot checks of respirable silica because the concentrations vary so much with production and wind. And I've showed that we could use area stations, but they're generally pretty expensive and not that accurate. But the Australian firm used a very low-cost dust sensor aboard their UAV and proved that it could be correlated well to a reference instrument. That, along with other work I've been doing on the development of real-time dust monitors, made me think of a new solution. Why don't we use a lot of low-cost area monitors? And while we know that they're inaccurate, we can send around a mobile robot with high-accuracy sensors to correct the information. So I introduced that new concept here. On the right, we have an industrial sand plant with wireless dust transmitters scattered all around. And on the left, we have a mobile robot with high-accuracy dust measurement equipment. The idea then is to send the robot around throughout the workday and stop at each of the sensors and collect its own reading. Since the robot has the true dust concentration, those values can be fed back to the network and correct the area stations. Let me put the concept I just described into a system diagram. The inputs to our system are things like weather conditions, production scheduling, and quantity. The end goal of the system is the improvement or application of effective engineering controls. We want to either demonstrate that we have a problem or reduce the ones that we do have. To visualize that, we need an interface. Software, likely cloud-based, that will enable us to view and interact with the dust sensing network. Inside the system, we have dust sources. These are machines, processes, and areas that are known to generate dust. We would then logically locate the area monitors in locations where workers spend most of their time and in high enough density that the major dust sources could be triangulated based on the data. The more area sensors, the higher the resolution that we can quantify the dust levels with. Unlike typical wearable monitors or larger stationary ground-based monitoring, these are intended to be low cost. I'm thinking of target of $500 to $1,000. So that was the whole system of area dust sensors and the mobile robot. On this slide, I'll focus more on the mobile robot itself. This is a system that still has its output of lower dust exposures, but now the inputs are obstacles that the robot must avoid. Much more on that in my full report. The robot system also has to interact with the docking station, and of course the low-cost area monitors. More than just dust measures, we want to know what's in the dust. For this, NIOSH has developed a technique using a portable infrared spectrometer that can estimate the percent silica of the dust while it's still on the filter. It's very quick, and the hardest thing is simply putting the cassette into the instrument. This brings me to why I selected the KUKA U-Bot. It has not only great terrestrial mobility for getting around the plant, but it also has a 5-degree of freedom arm for manipulating objects. I can use that arm to take the filters from the sampling pump and place them in the portable silica estimation instrument. The U-Bot is a great extensible research platform. It has the ability to carry 20 kilograms of equipment, and the 5-degree of freedom arm can manipulate objects up to a half a kilogram, both of which meet my requirements. I don't have time to go into detail about all the sensors and equipment chosen, but most of the importance is the dust correction instrument, like the mass-based real-time monitor in the upper left, the black object. This unit outputs the true dust concentration. Filters will be put from that device into the mobile infrared spectrometer to come up with the actual silica content. Stereoscopic vision or LiDAR sensors could be used for obstacle detection. Shown on the right is a screenshot of the VREP model I developed, and it shows the robot traversing from one area sampling station to another. So in summary, this is a robotic application which does not just replace or supplement human work, it makes possible what was not considered possible before, and that's the accurate and high-definition measurement of dust concentrations in real time. This data will be used to better understand where engineering controls need to be used to lower worker exposure. It's not enough to monitor silica exposure on the order of years. If there's a dust problem, we need to know right away so that we can get solutions installed. Silicosis is preventable. But to prevent something that you can't see, you need objective, real-time measures. I'd like to thank the professor and all our TAs and classmates for all your support and efforts this semester. You have no doubt empowered more than a few engineers to go back to their industries and apply robotic solutions that make a real difference. Thank you.